thank you, Simi ma'am. I'm very grateful to the coordinator of this course and the people at the NITTTR Chandigarh that they have given me an opportunity to deliver a talk on this topic. Well, this is a very recent area of the research work, especially in electrical engineering, because as you all know that in electrical engineering we are visiting a very recent change in the paradigm shifts in the deregulation of the electricity markets. So earlier we are having the VIU structure, vertically integrated utility structure of the grid. But now all over the world there is a number of changes are having occurred in the modeling of the whole structure of the power system. The power system which is generally composed of three things. As you all know, generation, transmission, and distribution. So mainly earlier it was the one government company which was owning the three utilities, three business. But now we have the different utilities which have been competitively they are doing the business in whether it is the generation sector, transmission, distribution. Mainly the restructuring or this process is also known as unbundling. So this process of restructuring and unbundling, it has been started with the unbundling of the generation sector, where we have a number of generation companies. For example, in Punjab, if we talk about, earlier it was the Electricity Board, but after the Electricity Act 2003, it is the PSPCL. And nowadays, many other generation companies, say if you talk about the Rajpura thermal plant, it's owned by some private company. So that's why the people, the politicians and the reformers, as well as the researchers, academicians, they are also thinking about the different kinds of problems which are occurring due to the restructuring. Although restructuring is very beneficial, but due to restructuring, one good thing which has occurred is that number one, it is a competitive environment, and number two, that the demand which was earlier the passive participant, it has now actively being involved in this business of say transferring the electrical energy from the utilities, from the generation sector, from the generation to the distribution. Now there is a concept of say demand management. So demand management has become possible only due to the fact that there is the active participation of the demand, right? So, but although the price become very transparent, right, and prices are now unbundled. Not only the three components which have been unbundled, right? Generation, transmission, distribution have been unbundled. Along with that, the different services are also unbundled. So, say in the earlier system, if we talk about the reactive power, so reactive power was bundled within the active power. But as far as this new environment is concerned, the utilities are paying separately for the reactive power, because the reactive power services, so they come under the ancillary services provision. Okay? Now, number of people are doing research based on the active power procurement, based on the reactive power procurement, except the other essential ancillary services. So one of the challenge with this deregulated environment is that reactive power is required to be managed. We call it reactive power management. Okay? And another challenge is congestion management. So I have done a lot of work on the congestion management. Congestion is a problem because now say that transmission system is being highly engaged due to the flow of the electricity from generation to distribution, and in case of say deregulation environment, the electricity can also flow back from the distribution side to the generation side. So transmission system is highly engaged. That's why there comes the problem of congestion of the transmission lines. Although congestion is a broad term, it does not depend upon only the loading limit of the line. It means that all the requirements for the operation of the power systems are not being fulfilled, because the power system is required to be operated under certain constraints. If we got those constraints under limiting conditions, when those constraints become limit, say for example the bus voltage is required to be operated between 0.95 per unit to 1.05 per unit. But if however we are not able to lie between that, this is also a one form of congestion. Another is that transmission loading limits. So transmission loading limits is a very recognized problem of the congestion in transmission lines. If we talk about say I'm coming on this my PPT, my presentation, that I'm going to present the things with this aim that power system deregulation and the electricity market, some introduction. Then the essential component of the power system deregulation and electricity market is the market dispatch. Earlier it was the economic dispatch. So in economic dispatch, the problem is that we have to minimize the cost of the generation. But now when demand has been introduced, demand is also giving its bits. Earlier it was the cost function, but now it is the bits. The generation is giving its bits, now demand is also giving its bits. So that's why in market dispatch, the objective of the market dispatch has now become the social welfare. So I will talk about the social welfare function, and then some new areas I will try to discuss. Then some optimization tools which are required specifically for the researchers, as well as these are required for the utilities, because utilities are also have to perform the market dispatch. Utilities are also have to perform the congestion management. So without the help of optimization or in general computational tools, it is not possible. So computational tools are always required. So researchers require these tools. I am working on some tools, so I'm going to discuss those tools which on which I am working, say on MATLAB, Matpower, and AMPL. These are the tools on which I am working, so it's better that I can explain these things. Although there is no limit of the optimization and computational tools available nowadays, as the universe is, as the universe is expanding day by day, all the things are expanding day by day. Research is also being expanded day by day. We are involved in new problems, and every problem has some solution. If there is no solution, then there is no problem. So it's a general quote. So it's very, I think it's very good thing for the researchers that they are getting new problems, because then they have got opportunity to solve these. So if I come to the introduction part of this market dispatch and congestion management. Conventionally it starts with the VIU structure, vertically integrated utility structure. Then the restructuring of electric utilities. It has converted the monopoly organizations into the competitive market entities. So the prevailing market structure is horizontally integrated. So this was the earlier structure. All the generation, transmission, distribution, these are being owned by some electricity board, single utility, and there is customers which are the passive participants. Now different entities have been introduced into the typically restructured power market. We are having the generation companies. A number of generation companies. Transmission company is more or less this is under the control of government utility. As if we see the Indian structure, it's a PGCIL, which is taking care of transmission, and distribution is again having different companies. Private players are also there in distribution. Government players are also there. So customers. Then one very important entity of the restructured power market is ISO, Independent System Operator. So this is independent system operator is managing the whole show. So whether it is the scheduling, whether it is congestion management, whether it is ancillary services procurement, ISO has the responsibility of performing all these functions. In certain countries, even the transmission planning is also being done with the help of ISO. Okay. Then another major and another important entity which has been introduced in the restructured power markets is the trade markets. Okay. So traders are say they are one time they are supplier, one time they are say buyer. So they can involve in the business of sale and purchase of the power, sale and purchase of the electricity. So if we go one step ahead of the deregulation, then we come to the smart grid. So if we talk about the smart grid, it is again the starting level is deregulation, but in smart grid there is the introduction of a number of renewable energy sources, because if the society has to get the clean environment, we have to more and more rely on the your renewable energy sources, whether it is wind, solar and others. And demand response is one of the key factor in the smart grid, right? So demand is giving its proper response. Demand, smart grid is having the characteristic of self-healing. So this has been done with the help of a number of demand response programs. Okay? Congestion management can also be done with the help of demand response program. And whenever there is a say need, the power can be flow from one side to another side, from generation to distribution, as well as the power can be, there is a reverse flow of the power from the distribution to the generation side. Whenever say I am having a rooftop solar power plant in my home, then there is a provision in smart grid that any demand which is having rooftop solar power plant, it can integrate its power, it can feed its power to the grid. So this again leads to the fact that the need of the power from on the transmission line has been reduced. So when the need of the transmission line flows has been reduced, it again leads to the congestion management. So information and power, the power, both the things can flow irreversibly in one direction to another direction and vice versa. Information flow and power flow. Basically, smart grid, it is the integration of the three branches of engineering electrical engineering, information technology, and the communication engineering. Okay, so we are having very large scope of the research work in smart grids. So we can have the collaboration with other branch of the students of another branch. So we can collaborate with the IT and communication people, because they can help us and we can help them to understand the problem. So because problem is of electrical engineering, but they can be solved with the help of the tools which are available in other branch of engineering. So smart grid is also having the very high response of the researchers. Here we are having the two power exchanges in India, which are generally doing the business of trading of the electricity. It is the Indian Energy Exchange. So these are their sites. So if you can visit their sites, you will gain the knowledge that how they do the market dispatch and how they do the congestion management. Basically, when I have visited their sites, what they are doing market dispatch, and there is a market clearing price, MCP, then they call it market clearing price. So whenever there is no congestion in the system, there is same price at all the areas. Okay? But if we are having the congestion in the system, say I have taken this map of the India from that site. So they have given MCP for this whole area when there is no congestion. But if in case of the congestion, they split the market. So one market has been split into different markets. Each market is having depending upon certain area. If you say in the website, if you click at some area, it will give its MCP. It will give its area clearing price. So area clearing price becomes different in case there is congestion in the system. But if there is no congestion in the system, the whole market is having one common MCP. But due to congestion, the price can become different. So this is the one of the particular aim of my PPT, that I want to explain here the MD problem, market dispatch problem. I will consider one small system which I have taken from a research paper, and then with the help of a tool, I will show you that how we can solve it and how we can find out the price and how the price become different under congestion. Okay, so that I will do here. So these are the different trading arrangements which are available in the deregulated environment: mixed generation model, single buyer model, pool model, bilateral, multilateral contract model, and combination of the pool and bilateral, multilateral contract model. This is actually these trading arrangements are like that. Starting when the deregulation has been started, the process of deregulation has been started. First, it was the mixed generation model. Then, when the deregulation is further advanced, then becomes single buyer model. Then further advanced, become pool model. Further advanced, it becomes bilateral model. And now pool model and bilateral, multilateral model, they are existing. Pool means we can purchase the electricity from a pool, from a combination of the utilities. With the help of trading arrangements, we can buy the electricity. And bilateral, you all know bilateral, and what is bilateral and multilateral? Bilateral means a demand or a load center, it makes a contract with the generation. So there is a one-to-one contract between generation and demand. They can set their own price for the purchase of electricity. They can tell that, okay, I will purchase say 100 megawatt at this price from you, and they will tell their contract to the ISO. Okay, so ISO will then provide what we call transmission open access. So transmission open access, the concept of transmission open access is that whenever there is arrangement, bilateral arrangement between seller and buyer, the responsibility of ISO is that ISO will take care of the transmission. It will take care of the power flows. It will take care of the losses. It will take care of the reactive power. And then for every service the ISO gives to the seller and buyer, it charges it accordingly. Now, how the ISO has to charge for active power losses, how the ISO has to charge for the reactive power management, how the ISO has to charge for, say, providing other protection services. Okay, that so those things are now up to now those things are not settled well. So there is scope of researchers that we can do research that no, this method is okay. Then other researcher can say no, that method has this problem, and we are having some more say more transparency, more accountability. So here we are having the scope of research work. So this is the pool model. So GENCOs, transmission company, DISCOs, consumers. ISO takes care of the transmission flow. ISO takes the bids from the generation companies and distribution companies. Distribution company can tackle the customers. Okay. So I will do the consider one example based on the pool-based electricity markets. So pool-based markets, these are competitive markets which takes care of the GENCOs and DISCOs. GENCOs sell electrical energy to the consumers. Consumers are the distribution companies. Distribution companies purchase bulk power and they further sell it to the industrial, commercial and domestic consumers. So role of ISO. Role of ISO is to prepare a generation and demand schedule. So this on day ahead basis. So one of the major role of ISO is scheduling. So this is known as day ahead scheduling. So for in India we are having 15-minute schedule of the next day. You can visit the site of say the central utility which is involved in this business, NTPC, other sites you can visit, and you can see the 15-minute schedule is available for the next day. Although sometimes we are having hourly or half-hourly schedule, generators can bid for their generation cost on their own or on their behalf. GST, traders can also bid. So traders has a multiple roles. Traders can be involved in the sale and purchase of electricity. Traders can give the bids on behalf of the generation companies, or generation companies can hire their services. So there are supply bids which the GENCOs are giving to ISO, and LST, load serving traders. So LSTs are the pool consumers which submit their hourly or half-hourly. Sorry, here it is not supply bid; it is a demand bids to the ISO on day ahead basis, right? So this is the basic procedure. Supply or cost bids provided by a GENCO. Yes, this is the minimum asking price which it would accept for supplying a particular amount of power. So actually there are two types of arrangements. One is called uniform pricing arrangement, and another is called pay as bid pricing. Okay. So basically uniformly pricing structure is more prevalent. In that case, what happens that whatever is the bidding price of GENCO of different generation companies, and whatever is the bidding price of different distribution companies, they have to pay the distribution companies have to pay a uniform price, irrespective of their bid price. Similarly, irrespective of their bid price, generation companies are getting a uniform price for their supply. So generation companies are getting the price for their supply of the generation, and distribution companies are getting the have to pay the price for their purchase, for their consumption of the demand. Okay? And this price is uniform. So this is the uniform bidding. But in another case, pay as bid. Whatever you pay, that is same as your bidding price. But uniformly pricing scheme, that is more prevalent. So for the generation companies, it is the minimum price. The bids of the generation companies, the minimum price which they are asking for the sale of their power. And for the demand, demand or benefit. For demand, it is the benefit bids, and for generation, it is the cost bids. So generation has to bid as per their cost, and demand has to bid as per their benefit. So demand or the benefit bid of a consumer is its maximum willing price, which it would pay for consuming a particular amount of power. So maximum what I can pay. Okay? A demand maximum what I can pay, but actually the actual price which I have to pay will be less than or equal to my willing price. For a generation company, the price I will get will be more than or equal to the price which I am bidding. Right? I will explain it with the help of a diagram. So I also determine the generation and demand schedule as well as LMPs. So LMP is the locational marginal prices based on the, this is objective function, maximization of social welfare subject to system operational and security constraints. This is the screenshot of Power World Simulator which I have taken for the 9-bus system. This actually represents the load flow. So what I say, for deciding the price, operational and security constraints are required to be met. So operational constraints commonly in electricity, although there is deregulation of the electricity, but the business of the electricity as a commodity, it is different from other commodities. The difference is that at every moment in real time, whatever is the generation, that is required to be balanced with the demand and the losses. Okay? So we cannot say that, okay, we are generating at one period of time and we will consume in other period of time. At the that instant, whatever is the generation, that is required to be met with the demand and losses. And this is the operational constraint of the electricity market, of the, this is called power system operational constraints. So load flows. So power flows or the load flows are generally used to meet these constraints. So power flow says that our system should be working under balanced conditions. So this is the one of the screenshot which I have taken from Power World Simulator. So power flow, all the electrical engineering students must know that power flow is the solution of simultaneous equations which determine the state of the power system. So what is the state of the power system? That is very important. The state of the power system, it is represented by the voltages and the angles. Okay, V and angle delta, bus voltage magnitude and bus voltage angle. So V and angle, so they determine the state of the power system. So state of the power system can be determined either by the offline power flows, or nowadays by using PMU placements, that what we got online measurements, and we apply the least square method here to determine the state of the power system. So particularly that is known as state estimation, SC. Okay. So power flow is very basic tool which is required to determine the, so you know all that there is a Newton-Raphson method, Gauss-Seidel method, and then fast decoupled method. They are all used to obtain the load flow or power flow. Now after power flow, we go for the optimization. So optimization is a process which is required everywhere. Even the, you know that the present techniques of optimization, they come from the birds and fishes. The nature is also doing optimization. So similarly, optimization is required in every field. In power system, it is also required. I think we were here at the power flows, and we are discussing that optimization is required, and naturally optimization is prevailing everywhere, whether it is any field of engineering, whether it is some nature, or whether actually by habit we are doing the optimization. So the latest techniques are coming from, say, natural, say, birds, fishes. So optimization is also required in power flows. Optimization is already done for the generation cost actually. So OPF basically means optimal power flow. Optimal power flow for generation cost, and minimization, cost minimization, and it is subject to the operational constraints. Operational constraints are power flows. So power flows can be determined by the solution of simultaneous equations. Then after OPF, after optimal power flow in the deregulated environment, it is a market dispatch. So market dispatch, all the other things are same, but what happens here that now the generation companies are giving their bids for the cost function, and the distribution companies also giving their bids. So the distribution companies are not giving their bids. It means the demand is inflexible. So demand is fixed. But here, when the price are now in the hands of the market entities, in the hands of the demand can control the price actually. So the basic aim of deregulation is that demand is able to, because you already know that customers are God everywhere. So for the business environment, so these are the customers which decide the price. So social welfare maximization actually means, in competitive market environment, social welfare maximization means maximization of the consumers as well as supplier surplus. This type of market design, which is also termed as double auction market design. Single auction means only generation is bidding. It is single auction. When generation and demand both are bidding, it is called double auction bidding, and it is used in some markets of the USA. PGM, New York, New England, Midwest, California, they are using these market structure. So seller bids consists of price offers and quantity of the power to be supplied in each hour. So specifically, the stack of price offers and megawatt levels. So whatever is the megawatt level and at which price that megawatt level or that megawatt quantity is being offered by a generation company, at what price, this is its bid. It takes the form of staircase price offer curve, which is continuously increasing. So this is the seller cost function is piecewise linear, which is obtained by integrating the price over the megawatt level. So this type of seller bid is used in electricity markets. Say for PG1, up to PG1, the company says that I will offer the PG1 quantity at a price of P1 per megawatt hour. Then from PG1 to PG2, that PG2 minus PG1, this quantity can be made available at a price P2. Similarly, the PG3 minus PG2, this quantity of the power will be made available at the price P3. So this is a seller bid. So this is a bid. The bid is between price and the quantity. So from this price quantity curve, what we can obtain is the cost function, supplier cost function, by integrating price with the bids. So supplier cost function can be obtained from its bids as the area under the curve. Area under the curve is always given by the integration of y over the x-axis. So these are the mathematical relations which decide the cost function of the power generation, right? Say if the PG is between 0 to PG1, so simple multiplication of price with the quantity. Then if PG is between PG1 and PG2, then first say the first part plus second part, okay? Then if the PG is between PG2 and PG3, then first part, second part, and then component of third part is also included, right? So what I want to say that if say my power generation is up to this point, then this is my cost function, but including the other components also, so cost function is increasing. So if I plot the seller cost function from that those mathematical expressions, so cost function is increasing. It is also known as convex cost function, right? Now in case of cost bids, we start from the lower one, right? As we increase the power to be supplied, my unit cost is increasing. But the reverse happens in case of buyer's bid or demand bids, right? If the buyer bids can be flexible or inflexible. Inflexible means whatever is the price, there's no matter, but I have to purchase the power at any cost. If I'm say that I have to purchase this much of the megawatt at any cost, then it is a inflexible bidding. But if I say that no, I'm flexible about my bidding, my power to be purchased and my price which I will pay, then it is flexible. So flexible in both terms, in price as well as in power purchase. So buyer, now other thing is that some portion buyer can say, okay, this much this portion is flexible and this portion is inflexible. Yeah, I have considered this approach in one of my research, that I have considered that out of 100%, 85% is my inflexible demand. I cannot change my demand, but 15% I can change. So I can bid. There is a I have taken this concept from an earlier paper, that some portion is inflexible, some portion is flexible. So that flexible portion I can change. That flexible portion I can shift from high price time period to the low price time period, and that becomes one of the method of the congestion management. Okay, so if I am able to shift my load from high peak period to lean periods, ultimately what happens that load profile will become flattened, and this is a very good thing for the transmission companies, for the utilities, right? So utilities make use of diversity of the power structure, load structure. Inflexible bid is also called the price taking bid, and flexible bid is called the price responsive bid. So this is the price taking bid. Whatever is the price, no matters, but I have to consume this much of the power. So whatever is the rise in price, demand is fixed. So this is price taking. So this type of bid is not so useful as far as the congestion management is concerned, but this is the price responsive. When the demand is increasing, I am reducing my price. Earlier, when the demand is low, my price is very high because the availability is low. The availability is low, ultimately price will rise. So this is a demand supply curve, normal demand supply curve. Whenever the availability is high, then price will reduce. When the availability is low, the price will increase. That's why at the low availability of the power, price is high. But as and when the availability of the power increases, my bidding price reduces. Okay. So the very first megawatt I can take at very high price, but as more and more megawatts are available to me, then I will say that no, I will pay less price. Okay, because initially some amount of power is essentially to be taken, is essentially to be consumed. But as the power quantity of the power increases, then I can have some plus and minus. Then I can shift that 15% of the power to some other period. So there I can say, okay, that last 15% or last 10% or last 5%, I will take at some very low price. Okay. So price responsive bidding. The same mathematical equations now in terms of price and the power demand can be used to obtain the area under the curve. Area under the curve becomes the buyer benefit function. So here the total area under the curve becomes the buyer benefit function. So buyer benefit function corresponds to the price responsive bid is again a piecewise linear function. So this type of this is known as concave function. So this type of function is obtained, benefit curve is obtained. Now in case of electricity markets, instead of using the piecewise linear buyer bids are more popularly used. This is due to the fact that it is required to be modeled very easily. So what happens in case of when we solve some problem, we do make certain assumptions, and that assumption should be close to the practical, and with that what happens that our computation efforts are reduced, right? So due to the ease of the modeling, the buyer's bids is represented in linear form. The price to be paid by a bidder decreases monotonically with increase in the power consumption. So instead of using staircase, we can use these types of bids, that price is reduced with an increase in power demand. Okay. So buyer's benefit function can be obtained from the area under the bidding curve. If we do mathematically, we can integrate, which gives the benefit function. And this benefit function comes in the form of ABC coefficients. Actually, when we do the economic dispatch problems, we have the cost function represented in the form of ABC cost coefficient. So APG square plus BPG plus C. So here you get this value as minus 0.5 AR PRT square. So this is your A in case of demand, but it is a minus in nature. And this lambda max, it is the B. So it comes APG square plus BPG. Board is not available. But actually a teacher is requiring some board every time. Because we are generally having the habit of doing the teaching with chalk and boards, so that is always required. So this price and power demand can be obtained as a distribution company's benefit function. Here you can see that minus AR. So minus AR represents the slope of the curve, right? So the buyer bids are negative or having negative slope. Benefit function is always increasing. So if we talk about the benefit with respect to the power demand, it is always increasing. This is another kind of bids which is responsive as well as shifting. So PRDS bidding. So these bids have been introduced in day ahead market in literature in 2009 by this paper, Su and Christian. Under PRDS, price responsive and demand shifting, both things are there. So because in case of price shifting, I am not in case of price responsive. In case of price responsive, the price is responsive, price is flexible with respect to the demand is flexible with respect to the price, but it is not shifting. Because say I am saying that I will consume 10 megawatt at say 5 rupees per megawatt hour, but market price is 10 rupees per megawatt hour, then I'm not able to consume that power which I have paid. Okay, are you understanding that? Say I am consuming this much of the megawatt at this much price, but that bidding price is less than the market price. Then what will happen to my demand? My bid will fail. I'm not able to consume that demand. But in case of our price responsive demand shifting bidding, I'm able to shift that part of the demand to another periods. So under PRDS bid, a buyer can increase or decrease its demand in response to the market price, as well as it can shift its demand from periods of high market price to the periods in which market price is comparatively low. So this is a particular characteristic of the PRDS bid. Price is responsive as well as its shifting. So under PRDS bid, a buyer can extend its bids to multiple periods. This is not a power bid, actually, this is energy bid. So buyer can extend its bid to multiple periods to maximize the benefit over the complete scheduling period. Okay. Under PRDS bid, the buyer bid for energy over the complete scheduling period instead of power. Okay, this is the energy bid. The simplest form of the PRDS bid is that energy consumed by the bidding buyer during complete interval scheduling. Complete scheduling interval is of 24 hours. So 24 hours scheduling interval, that power can be consumed even in a single period. Even in a single period or 1 hour at the maximum. So this verbal statement, this is a verbal statement actually, that I can consume the whole PRDS power in the 24 hours, or I can consume whole power in 1 hour. So my power consumption extends from 1 hour to 24 hours. And when I write this in the form of mathematical equation, these two mathematical equations explain my statement. Right? If the board was available, I can give you more conceptual concept of how the PRT and delta T are obtained. So PRT is the power, ER is energy, delta T is scheduling time of one interval. Okay. So this delta T is a member of the total. Capital T is the 24 hours total scheduling period. Delta T is 1 period. So power is total energy divided by delta T, and summation of the power over delta T is also less than equal to energy. So it means that this total summation is equal to energy, and power in single period is also equal to energy. Okay? So power in single period multiplied by that time is equal to energy. So what I want to say that, say if there are 24 hours, so I can consume the power extended over the 24 hours, or I can consume that in single period. So this is only for that 15% of the component out of the 100%, not for the whole power, because it is small component which I can extend. So this is one of the method which I have used in my paper for the congestion management, because actually I have taken this concept from this paper, Su and Christian 2009, they have generally introduced this concept, but not used for congestion management. But I have done, I have taken the concept from them and used for the congestion management. And this paper I have got published in IEEE Transactions on Power Systems in 2011. Okay, optimization is always there. Optimization is required when we go for the actual problems in power systems, when we go for the scheduling, when we go for the congestion management, when we go for the minimization of losses, when we go for the ancillary services procurement. So a researcher has to go for the optimization. Okay, so optimization, I will give you some concept, some introductory concept, because power system researchers already know how to apply optimization, but I will give you the small overview. Optimization means to obtain the best results under given circumstances. Optimization is needed everywhere, whether it is engineering, management, organization, homes, shops. Generally, I take one of the class of the optimization techniques in my institute, Guru Nanak Dev Engineering College, Ludhiana, and I generally start with one sentence that even when you prepare a tea for you, then even then the optimization is also required. So making a process of tea is also a process of optimization, because in that problem you are having again some objective function, some constraints. Say tea should be very tasty, it's objective function. Okay, or you should prepare the tea in very less time, this is objective function, but there are certain constraints. So optimization means actually we all are using the concept of optimization. Optimization is in our habit. So we all are doing optimization knowingly or unknowingly, right? But there is a scientific way of applying the optimization, and we will use that way, that systematic way of optimization, to solve our problem of market dispatch, optimal power flow, and congestion management. So there are two broad steps of the optimization which are required, irrespective of any field problem, within engineering, management, any field. The two steps are that we have, number one, we have to develop a mathematical model. So that mathematical model is also known as problem formulation. So first of all, for applying the optimization, what is required is problem formulation. And in order to have a problem formulation, we have to decide basically three things. We have to decide what are our decision variables. Then we have to decide what is my objective function. Then what I have to decide the constraints. If I am sure about these three things, then there is nothing in the optimization. Okay. Decision variables should be clear to me. So decision variables are those variables which are going to maximize or minimize my objective. Okay. Every function is made up of functions. Y is equal to fx. So y is a function of x. So y can be objective function, or y can be the constraint functions. So constraints are also functions. Objective is also function. X is our decision variable. So we have to decide x. What is my x? So when I decide my x, then I can use that x to define my objective function. Say cost. Cost is my objective function. So cost is required to be minimized. Time is my objective function. Time is required to be minimized. Benefit is my objective function. Benefit is required to be maximized. Right? So utilization of the resources, it is my objective function. So reliability, I want to increase the reliability. It is my objective function. So the function which is required to be minimized or maximized is called the objective function. And objective function is a function of variables. So those variables are decision variables, right? And constraints, certain environmental, certain physical conditions I have to take care. Say in electricity market, I have to take care that power should be balanced. Whatever is the generation should be demand plus losses. At every node, the power which is input, power which is entered, minus power which is leaving should be equal to the power which is flowing. Okay, so power entering, power leaving should be equal to power flow. So that those constraints are required in case of power system operation, balanced power system operation. No, so when I am able to develop a mathematical model, then my first step is over, and then we have to select an appropriate optimization technique. Number of optimization techniques are available nowadays, and these techniques are increasing day by day, right? Because new things are coming into the optimization research. So that's why in my when I do the formulation of the problem, when I do some research, I basically concentrate on the first step, that problem formulation, because I don't go for the second, because there are number of things, number of techniques are available. So instead of developing new technique, develop a new problem, solve a new problem. So that's why I just concentrate on the first step more. This type of mathematical model, general form of the mathematical model is required. Say fx is a objective function, x is the decision vector. Decision vector consists of a number of decision variables. It means decision variables x1, x2, x3, xn. N decision variables are there, so they give me a objective. They give me a decision vector, right? And this decision vector gives me the function. Then I'm having the different types of constraints. Generally, this Cx, it represents the non-linear inequality constraints. Then Ceq, it represents the non-linear equality constraints. And Ax is less than equal to b. Ax less than equal to b, it represents the linear inequality constraints. And here I'm having the equal to, not less than equal to, a equal to x equal to b equal to. So a equality into x is equal to, this less than should not be there, a equality x equal to b equality. So this represents the linear equality constraints. So constraints can be of broadly of two types: inequality and equality. Inequality are those which are having less than equal to or greater than equal to sign, and equality are those which are having equal to sign. And then non-linear, then inequality constraints can be linear or non-linear, right? And equality constraints can be linear or non-linear. So four types of constraints are there: non-linear inequality, linear inequality, and then non-linear inequality and linear inequality. Okay, so four types of constraints are there, right? Some lower bound and upper bound for the decision variable. Say my voltage is there, voltage is my decision variable in case of power system operation. Then there is lower bound on the voltage, that 0.95 per unit is my lower limit, 95%, and upper limit is 1.05 per unit. Okay, so I have to operate my system with a voltage regulation of 5%. Similarly, if power generation, Q generation, these are the decision variables, then for a generator, power can be generated within some minimum and maximum limit. Okay. Then for congestion management, I take care of transmission loading limits. So transmission flow, so that is also required to be fall within the limit. It cannot be become greater than the maximum limit. So now I have to start with this market dispatch problem by considering one example. So I will consider here two types of market dispatch: DC OPF and AC OPF. So DC OPF means there are certain simplifying assumptions which makes my problem simpler. Okay, that makes my problem linear. Actually, the constraints become linear. So I will more concentrate on DC OPF here, because I can easily make you understand what is DC OPF, and I can easily solve it also. So for solving the AC OPF, I will show you that the Matpower. I think all of you must know Matpower software, that is developed by the Dr. Ray Zimmerman, that can solve AC OPF, DC OPF, that can even solve the problems of including the effect of benefit functions, including the effect of capability curves, right? So this problem I have taken from the paper of the actually GADRA paper, which I have taken one example for congestion management and pricing. So I have to start with this problem. If you have up to now, if you have some questions that because now I have to start with the actual problem and how to model it and how to solve it. So the objective function of the electricity market dispatch, as I have already said, that cost function of generators and the benefit function of the consumers, and the constraints. The electric power system are subject to some inherent constraints. Supply and demand is balanced, and the transmission lines are having limited capability of the power flows or the line flows. So this is one of the example which I have taken from the paper, and this example is for the taken for solving DC OPF problem. So some certain assumptions: our line resistance are neglected, then reactive power flows are not considered, then voltage magnitude is 1 per unit, load angle differences are small. So if you look at this problem, the cost function of this generator at bus number 1 is C1 P1 square dollar per hour, and cost function of the generator at bus number 2 is this 1.675 P2 square dollar per hour, and this is the benefit function B1. So these values I have taken from that paper. B1 is the I should call it B3, benefit function of the demand at the bus number 333 P3. So P3 is the power which is drawn out of the bus. Actually, generally we take the power input, but here P3 I have taken the power out of the bus number 3. And this is a 3-bus system, base MVA 100. Line susceptances I have taken from that paper. B12 is the line susceptance of the line connected between 1 and 2. B23, the susceptance, line susceptance of the line connected between 2 and 3. Similarly, B13, and their limits, power flow limits I have taken. P12 maximum 8 megawatt, P23 maximum 20 megawatt, P13 max 30 megawatt. So this is the data which I have taken. P1 is the power generated or power injected at bus number 1. P2 is the power injected or generation at the bus number 2, and P3 is the power drawn, not injected. It is the power drawn at the bus number 3. So based on this data, the social welfare function can be formed. Social welfare means the benefit function of the demands minus the cost function of the generators. So social welfare function is like B3 P3, benefit function of the bus demand at bus number 3, which is a function of the power demand minus cost function C1 as a function of P1 minus C2 as a function of P2. Okay, so the cost function of the generator at bus number 1 and generator at bus number 2. But in the standard optimization problem formulation, instead of considering the maximization, what we consider the minimization of the objective function. So the minimization of the objective function is taken. Our problem is maximization. We convert it into the minimization problem by taking minus of the SW. So cost C1 P1 plus cost C2 P2 minus benefit B3 P3. Ultimately, if we minimize this function, then this function will get maximized. Now C1 P1, C1 as a function of P1 is written, C2 as a function of P2 is written, then benefit as a function of P3 is written. So this is my objective function, right, in the minimization format. Now in DC OPF problem, power flows can be simplified in this form. Pij is equal to Bij theta I minus theta j. But actually, in the actual problem, what we call it Vi Vj over Xij sine theta I minus theta j. So because Vi are 1 per unit, okay, sine theta is approximately equal to theta when the theta is low. So we can by considering the assumptions, what we do, we make it linear. This is the linear equation. So Pij is equal to Bij theta I minus theta j. So that's why what we get P12, we get all the values, all the power flows from bus number 1 to 2. So what is P12? P12 is B12 theta 1 minus theta 2 using this equation. So B12 is 1. So theta 1 minus theta 2, and then P13 is equal to B13 theta 1 minus theta 3. And then B13 we have taken, then B23 we have taken for P23. P23 is equal to B23 theta 2 minus theta 3. So what we have obtained power flows. We have obtained the power flows P12, P13, P23. Now, from the power flows, what we can obtain is the bus powers. Bus powers, what is bus power P1 equal to? If you look at this system, the bus power P1 is given by P12 plus P13. Power which is flowing from 1 to 3 plus power which is flowing from 1 to 2. So just we add P12 with P13. So what we get? What we get? P1 is equal to 1.5 theta 1 minus theta 2 minus 0.5 theta 3. So similarly, when we obtain P2, P2 is equal to P21. So bus power which is injected at bus number 2 is P21 plus P23. Now already we are having the values of P21 and P23. So we can obtain the bus power P2, right? So when we got the bus power P2, we go for the P3. Actually, if the power P3 is the injected bus power, then P3 can be written as P31 plus P32. But now it is not injected. It is the power which is taken out. Right, so P3 is the power which is taken out of the bus number 3. So if it is the power which is taken out of the bus number 3, then P3 will become equal to P13 plus P23. So P13 plus P23. So P13 and P23 values I have put here, which I have taken from the earlier slide. And we get the P3 in terms of theta 1, theta 2, theta 3. And when I have got the powers in terms of theta 1, theta 2, theta 3, I can write these equations in the matrix form. So P1, the P1 equation, this is the P2, this is the P3. So P1, P2 and P3 can be written in the matrix form as a function of theta 1, theta 2, theta 3. But the requirement of the power system is that one of the buses is required to be taken as the slack bus. So theta 1 is a 0 reference bus. So theta 1 is made 0 here. P1, P2, P3 is written in terms of theta 2 and theta 3. Okay. So theta 2 and theta 3 are my state variables. P1, P2, P3 are my control variables. So these are the power flow constraints. Then other constraints, the power flow constraints are in the form of equalities. Here we are having the equal to sign. And then we have the line flows, transmission line loading limits. So transmission line loading limits are in the form of inequalities, inequality constraints. So power flow P12. Inequality constraint is that power flow P12 should be greater than some minimum value, greater than equal to some minimum value, and should be less than equal to some maximum value. 8 megawatt is the maximum limit which I have considered here. So 0.08 per unit. All the things are here are in per unit. I convert the various values in per unit by dividing with the base. So P12 should be, say, greater than equal to minus 0.02 and should be less than equal to plus 0.08. So minus of I have taken because the direction of power flow can be either from bus number 1 to 2 or it can be from bus number 2 to 3. Sorry, either from bus number 1 to 2 or from bus number 2 to 1, right? So then I have converted this single constraint into two constraints. P12 should be less than equal to 0.08, and if P12 is greater than equal to minus 0.08, we can write it as minus P12 should be less than equal to 0.08. Okay. So if say x is less than 4 and if x is less than minus 4, okay, then minus x is written as greater than 4. Now P12 is put in terms of theta 1 and theta 2. Theta 1 is a slack bus power, slack bus angle. Theta 1 is 0. So P12 is minus theta 2 actually. So from earlier equation, this is P12. P12 is theta 1 minus theta 2. When I take theta 1 0, P12 becomes minus theta 2. So that's why what I can write here, P12 in terms of theta 2. So P12 is minus theta 2, which is less than 0.08. And minus P12 is plus theta 2, which is less than 0.08. So similarly, I can write all the power flows. There are this is 3 line system, right? This is a 3 line system. In the 3 line system, there will be 3 equality constraints corresponding to the power flows, and there is 6 inequality constraints because for 3 lines, for each line there are 2 less than and greater than. So for each line we are having 2 inequality constraints. Total 6 inequality constraints are there, right? And here, how many decision variables which we are having here? So as far as decision variables, okay, first I write the inequality constraints in the matrix form, theta 2 and theta 3. I have written the equality constraints P1, P2, P3 as a function of theta 2 and theta 3. Then I have written the inequality constraints in terms of theta 2 and theta 3, because inequality constraints, they are not the function of P1, P2, P3. The line flows are the function of voltages and angles, right? So voltage we have considered 1 per unit, and that's why line flows becomes the angles of thetas only. Now, if I come to my problem formulation of the DC OPF problem, already I have said that three things we require. We require number one, decision vector, right? So decision vector consists of decision variables. What are the variables which will decide that our objective function is minimum or maximum and the constraints are satisfied? So in this case, the decision variables which will decide the minimization and maximization of the objective function is, these are P1, P2, P3, theta 2 and theta 3, right? So 5 decision variables are required here for this DC OPF problem for 3-bus system. P1, P2 are the power generations. P3 is also a decision variable, which is a demand. Because we are considering the double action based, P3 is demand, which is not fixed. It is also variable. It is also say flexible. And theta 2 and theta 3, these are state variables which will decide that what is the state of the system. So 5 decision variables are required. We have to represent the objective function as well as constraints as a function of decision variables. My objective function, I have already written this objective function in terms of P1, P2 and P3. Now what I do, I take P1 as x1, P2 as x2, P3 as x3, theta 2 as x4 and theta 2 as x4 and theta 3 as the x5. So what I have done, I have generalized my decision variables from P1, P2, P3, theta 2, theta 3. What I have written, x1, x2, x3, x4 and x5. Because the objective function and constraints are written in terms of x. Because my computation require this. But why I'm doing this? Because this is the requirement of my computational tool. I will use the MATLAB for the solution of this problem, and MATLAB requires that the problem is to be presented in the form of x, decision vector. So objective function, which was P1 square. Now I have multiplied here 10 to the power 4 because P1 is in per unit, but objective function is in dollar per hour. So here this P1 multiplied with 100, it becomes 100 raised to power 10 raised to power 4. Okay, so 1.675 P2 square into 10 raised to power 4 minus 33 P2 into 100. Because in order to convert per unit into the actual value, power is to be required with the base. And then I have to represent the objective function in terms of x1, x2, x3 and x4. So P1 is my x1. So x1 square into 10 to the power 4. And P2 is my x2. And P3 is my x3. And in this objective function, x4 and x5 are not coming. What I do here, 0x4 plus 0x5, because I have to represent the objective function in terms of all the variables. Okay. Similarly, I have to represent the constraints in terms of x1, x2, x3, x4 and x5. So the first constraint is this is the first constraint. P1 is equal to minus theta 2 minus 0.5 theta 3. Minus theta 2 minus 0.5 theta 3 is equal to P1. And what is theta 2? It is my x4. What is theta 3? It is my x5. What is P1? It is my x1. So I have written the constraints in terms of x1, x2, x3, x4 and x5. Although the coefficients of x2 and x3 are 0. But I have to mention here. So similarly, then the second constraint is for P2. Again, I have made it for x1, x2, x3, x4, x5. Okay. Similarly, the third constraint. So 3-bus system, 3 constraints, and three equality constraints. So again P3, which is equal to 3 theta 2 minus 3.5 theta 3. I have written this constraint in terms of x1, x2, x3, x4, and x5. Now I have these constraints: first constraint, second one, and third one. And this is the matrix form which is required in terms of x1, x2, x3, x4, x5 decision vector. Okay. So this is the linear constraints which I have written in the matrix form, and this is a requirement of the MATLAB. MATLAB requires that this becomes A equality into X is equal to B equality. Okay. Why MATLAB is so popular? Because electrical engineering problems ultimately leads to some matrices, and matrices can be solved with the help of MATLAB. That's why there is a matching between the electrical and other branch of the engineering problems and the MATLAB. Similarly, all the inequality constraints are also required to be written in the form of decision vector. If you see at the earlier inequality constraints, they are only in terms of theta 2 and theta 3. So this is the inequality constraint which I am getting in terms of theta 2 and theta 3, because line flows are the function of angles only. They are not the function of power injections. They are written as the function of angles. But in case of representation of the inequality terms, equations, inequality constraints, I have to include other decision variables also. X2 and theta 2 is x4 and theta 3 is x5. But what is the role of x1, x2, and x3? Their role is shown by 0. So this is the complete matrix which shows that 0x1, 0x2, 0x3, minus x4, 0x5 is less than equal to 0.8. Okay. So all the 6 constraints are written in the inequality constraint form. Okay, in the matrix form representation. Now here I want to clarify one point. Only those inequality constraints are affecting our optimization solution which are violating, which are limiting. Okay. So what I say that, say power flow in line 1, 2 is 8 maximum limit 0x1, okay, 0x2, 0x3 minus 3x4 plus 3x5. So x4 and x5 are okay. So 6 I have having the 6 inequality constraints. This matrix is 6 into 5 matrix. This matrix is 6 into 5. This is 5 into 1. Okay, so overall it becomes 6 into 1. Okay. Magnitude of this actually these are taken as the capability limits. Transmission. Actually, I have taken this as a data from some paper. I have taken, but it can be taken as the stability limits basically. Basically, we take stability. Range is actually depends upon the fact that the difference of the delta should be less than 45 degrees. Okay? E12 is equal to EV upon X sine delta 1 minus delta 2. Okay? So P is equal to P max sine 45 degree. So 45 delta should be taken less than 45 degree. That becomes the value of the power flow which is acceptable between the any two PQ buses or IJ buses. Okay. Load flow is not required to be solved. It is embedded within the OPF problem. When we solve the OPF problem, okay, it will calculate the power flow values itself. It will calculate, but the thing is that So if we are calculating the DC OPF problem, it will give me only the real power flow, right? But it is not giving me the reactive power flow. In that case, what I can do that, okay, real power flow values are fixed after obtaining the DC OPF. Then I go for the then I go for the load flow. Then I go for the load flow and calculate what is the reactive power which will flow in the system. Okay. And in case I am directly going for the AC OPF problem, then load flow is already solved. It will give me the real power as well as reactive power. It will give me the V magnitude and delta.
Number of equality equations will be
In this case, in DC OPF, it is 3. In case of AC OPF, it will be 6. Because their P and Q, both power flows are required to be taken into account. Mm-hmm.
7 lines, there will be 7 equations, so we have to write all the 7 equations.
In that case, we can formulate the Y-bus matrix, and from Y-bus matrix, we can obtain that power flows. That can be written in terms of not for every line, for every bus. Equality constraints are required to be written for every bus. Line flow limits are required to be written for every line. Inequality constraints, inequality, less than equal to, greater than equal to, they are written for every line. But equality, equal to sign, they are to be written for every bus. So after we represent our problem in the matrix form, in the form of X, precision vector, then we can use the MATLAB for its solution. So MATLAB, which stands for the Matrix Laboratory, it's a special purpose high-level program for the multidisciplinary engineering and scientific computations. So many features, many benefits, user-friendly, huge library, plotting of the graphs, error bugs can be handled efficiently. You all know that MATLAB is very helpful. So when we develop mathematical model having the multivariable engineering problem, matrix representation has been found out. Okay, so this is the benefit. This is the basic advantage of MATLAB, that whenever we do the optimization problems, they can be end up with the matrices, and matrices manipulations, matrix computation can be easily done with the help of MATLAB. Every variable, any variable in matrix MATLAB is a matrix. So these are the 5 windows which are very helpful in MATLAB: command window, current directory, command history, workspace, editor window. There are a lot of courses this institute is doing for MATLAB. I generally visit your site, and there are a number of courses on MATLAB. I think you are very aware of the features of MATLAB. Even in undergraduate students, they are very much well doing in the MATLAB. So some of the commonly used matrix functions. Now I come to the solution of this optimization problem. And here I'm solving optimization toolbox in command line mode. And this command line mode, here different functions are available, different functions which solve the problem. But basically, I'm using very generalized function Fmincon. I think you must have heard this Fmincon. Fmincon is a function which can solve the function, nonlinear function under equality and inequality constraints. So what the Fmincon is doing, this is the basic command for Fmincon. Fmincon is a function name. X is the value of the decision vector which will get after optimization. This is output actually. And this Fmincon, it is a objective function which we have to specify. So when we write y is equal to fx, input, all these are the input arguments. Okay, all these are the input arguments which we have to specify. Okay, x naught, say x naught is initial guess, a and b. These are the linear representation of the linear inequality constraints. E equal, B equal T. These are the representation of linear equality constraints. So without any EQ, it is no, it is inequality, and EQ and BQ, these are the equality. LB stands for the, say, lower bound on the decision variables. UB stands for the upper bound on the decision variables. There are some non-linear constraints can also be given, but in our DC OPF problem, there is no non-linear constraints. All the constraints are linear. Equality as well as inequality, they are linear. Some options we can also specify. So what the Fmincon is doing, Fmincon attempts to find a constrained minimization of a scalar function. Means there is one objective function which is having several variables. We also call multidimensional problem, starting at an initial estimate. This is generally referred to as the constrained non-linear optimization, or also called NLP. Simply NLP is a very popularly used term. Non-linear programming, LP linear programming, NLP non-linear programming. Then there is MIN, NLP mixed integer non-linear programming. But here we are using this non-linear. Objective function is non-linear. So some variants of the specification of the input arguments. Now I want to go to the actually my MATLAB environment. Can I press escape to go to the another? Actually, all these constraints and objective function I have written as some M file. When we solve the optimization problem, actually we need two basic things. One is the main M file, another is a function file. You know this. So I have different cases of this system. I will explain that how this problem can be converted into single auction system. When demand is not responsive, then demand is responsive. So this M file, if you are able to see this M file is used for the DC OPF problem of 3-bus system. I am having the 5 decision variables. X naught, this is X naught which specifies the initial guess. Okay, initial guess for P1, P2, P3 is 1, and initial guess for theta 2 and theta 3 is taken to be 0. Then I have represented A matrix, just taken from my A matrix, which I have explained in the PPT, and I have placed here, right? Then B. If you see, directly I have taken the A and B. This is A, right? I have placed here. This one. This one is A. And this one is the B matrix. Represent the non-linear equality constraints. Then E equal and B equal. This represent the equality, linear equalities. I have taken these from the PPT. This one. And placed here. Lower bound. LB stands for the lower bound. Okay. So lower bound for the decision variables for all the powers. Power cannot be negative. So lower bound for the powers is 0. And angle can be negative. Theta can be negative. So lower bound for the angles is minus infinity, minus infinity. Otherwise, we can take the limit minus 45 degree, minus 40. Because the lower actual value of power, theta is coming out to very close to 0. So we can also assume minus 45 degree, but if we take minus infinity, then also it's okay. Regarding inequality constraints, we can consider all the inequality constraints as well as only those inequality constraints which are binding in nature, which are whose value coming out to be limit in touching the limit. Because my OPF problem cannot allow any inequality constraint to go beyond the limit. The power flow between line 1 and 2 is 8 megawatt. Then at the most, power flow between line 1 and 2 can be come out to be 8 megawatt, but it cannot go beyond. Okay. For example, if the power flow between 1 and 3 line and 2 and 3, it is not touching its limit, then that inequality constraint is of no use in optimization problem. Okay. Then actually the value of mu, when we form its Lagrangian function, you all know, optimization person already know that Lagrangian function is made. Okay. So Lagrangian function is objective function plus lambda into the equality constraints plus mu into the inequality constraint. So mu into the inequality constraint. So mu is existing, is positive only when inequality constraints are binding. If inequality constraints are not binding, mu is 0. It means that inequality constraint is within limit. So that can be avoided here. Okay. If we already know that these constraints are binding, then we can include only those. Then I have made this objective function file. This is the objective function. It is a function of x1 square, x2 square, and x3. x4 and x5 are not coming here, so I have not included. So all the powers and angles are to be written in the form of x. So this objective function, a function file is having the same name as the name of function. Okay. So this is the function file. The name of the function file is objf_fun, and the name of the function is also objf_fun. So this is required. So this is required to solve optimization problem. We have to have all these things. Actually, all these things are available in the help in the MATLAB. I'm not means telling you something which is not available. Okay, all these things are available, but the only thing is that if you means after listening this, your time will be shortened. You can grasp all these things by yourself, but you will find one way to go through. Okay, so in that case, you can the help option is always available in MATLAB, and some examples are also given there. Not of DC OPF problem, but general problem. So I am solving a DC OPF problem, which is specific problem. So this objfun function is taken from this function file. Okay, so this is a f function which is obtained, and it will put here, and it will solve. When solving this, we have to the one way of executing the problem is that write the file name on the command window and just execute it. So exit flag is 5, which says that problem is solved. Some options, the option which has been by default specified. We have not specified the option by ourselves, but some default options have been specified, which become satisfied. And there is one inequality constraint which become binding. And this is a value of x, what we're getting. Okay. 0.15 per unit is the P1, 0.10 per unit is the P2, 0.25 per unit is the P3, and minus 0.08 radians is the angle theta2, and minus 0.14 is the theta3 radians. This is the f value. So it's coming out to be negative, because what we have done, we have taken cost first and benefit after that. So this is negative. The social welfare will be 432.5, which is positive. So we are getting some value of lambda also. Lambda can be obtained from this workspace. So actually lambda is very important. It specifies the price which is required to be paid by the demand and which is required to be given to the generators. So this is the value lambda for the in research paper it is generally termed as LMP, locational marginal price. Okay. This is in per unit. We convert it into dollar per megawatt hour, as the data is in dollars and megawatt hours. After solving the problem, the solution of the problem comes numerically, but it's better to understand in the form of a figure. The values I have written here. So lambda 1 represent the price which the generator number 1 will get. Okay, lambda 2 is the price which the generator number 2 is getting, and lambda 3 is the price which the demand at bus number 3 has to pay. Okay, and from that price we will find out the say cost function of generator and the demand function of the benefit function of the demand, and we find out the social welfare. And only one inequality constant is binding, so which says that the power which is flowing from 1 to 2, it comes out to be 8 megawatt. Okay, so in this problem, so one constraint is coming out to be binding. Now, in order to understand it better, that how we can interpret this result, I have some slides that how to interpret these results. It's not easy to interpret these results from this case. So in order to interpret the results, how we can actually relate it with the practical cases, I have taken the 4 cases basically. These 4 cases are means it is it is depicting the two things. What is the effect of flexibility of the demand on the system? Number one. Number two, it is representing that what is the effect of congestion on the system. Okay, so in order to represent these effects, flexibility or responsiveness of the demand and the effect of the congestion on the system, first case I have taken that power demand at bus number 3 is fixed. It is 30 megawatt. It is not variable. Okay, then my problem will change. How the problem will change when the demand is fixed? In that case, my objective function will be only the cost function. Demand benefit function cannot be represented in the problem. Okay. Then because P3 is fixed. Now P3 is 30 megawatts, it's no more variable. P3 is 30 megawatts, no more variable. My number of variables become 4. P1, P2, which is the generation at bus number 1, P2 is the generation at bus number 2, and theta 2 and theta 3. Okay? No congestion in the system. If there is no congestion in the system, all the inequality constraints are vanished. If there is no congestion in the system, means there is no inequality constraints. Okay. Then again, I have solved this problem. For this, I have made a file case 1. So for every case, I have made one file, one main file and one function file. For example, this is the main file. A is equal to some null matrix, B is equal to null matrix, represent the inequality constraint. There is no congestion in the system. 4 decision variables. Okay. So accordingly, I have changed the objective function also. Objective function for case 1 is say objective underscore case 1, and I have also changed the objective function file. So now this is the objective function file. The effect of demand is not included. Right. So I can solve the main file. Yadra underscore 3 bus case 1. And it is again solving the problem here. 563 f value is the function value which is obtained after the solution, and this value is now representing the generation cost only. So x value is this. First two values are for P1 and P2, and then third value is for theta 2, and fourth is for theta 4. Again, in order to understand this, I have made this figure which represents now when there is no flexibility of the demand, what happens? Number one, actually the price becomes high. Number one, what happens that earlier the price was at say at bus number 3 demand says that I can maximum bid the $33 per megawatt hour. But if there is no flexibility, no bidding of the demand, then demand has to pay this price, $37.57 per megawatt hour. Why this happens? This happens because of the inflexibility of the demand. But demand is saying that I have to have the maximum, I have to have the 30 megawatt of the consumption. Earlier the consumption was reduced. Earlier the consumption was 25 megawatt for the demand at bus number 3. Now here the consumption is 30 megawatt. So that 5 megawatt can be flexibly adjusted. If there is flexibility in the demand, that we can adjust that 5 megawatt according to the price. There is no congestion in the system. Okay, so P12 can be even more than the 8 megawatt, 10.15 megawatt. Okay, so now the power demand, power generation values are also changed. P1 and P2 are also changed. Another thing, you can see that if there is no congestion in the system, what is lambda 1, what is lambda 2, and what is lambda 3? All are same. and this is the concept of MCP, market clearing price. So what we say that market has been cleared at this price, 37.57, because there was no congestion in the system. All the locations have to pay the same price. All the areas has to pay the same price. Okay. Now what happens in case demand at bus number 3 is now variable, flexible. Now demand at bus number 3 is giving its bids. What is the bid demand at bus number 3 is giving? It says that, okay, I can maximum pay $33 per megawatt. So whatever is the demand, what is the power you can give me, I can give me maximum demand of $33 per megawatt. Okay. Now in the case number 2, there is no congestion in the system. Line flows are not constrained. I'm considering only line flows as the congestion, as the one of the congestion, but other congestion are also there. But for the case of simplification, I've simplified this problem as given in that paper. When the demand is flexible, the flexibility of the demand will control the market price. Okay, so this is the case 2. If you compare it with the case 1, lambda 1, lambda 2, lambda 3, the prices at the 3 locations all are 33, maximum price which the demand can pay. Okay. Again, this is the MCP. Earlier it was I think 37.57, but here it is $33 per megawatt hour, which all the location has to pay. What happens that demand has been reduced. Earlier it was 30 megawatt, now it is 26. This is natural. If I have to pay less price, my demand will be cut. Right? If I am able to pay more, I am able to consume more. But the thing is that 5 or that 4 megawatt I can shift to some other time period. Now let us include the effect of congestion. Okay, so what happens? Now the demand is again inflexible. Demand is 30 megawatt fixed, but there is congestion in the line. So what will happen? So again I have made some changes, and there is case 3 in my M file. There is case 3. So say P3 is 30 megawatt, but it has to pay how much? $45.51 per megawatt. So this is the effect of congestion. If the demand is fixed and there is congestion, the price at the demand bus will drastically increase. Okay, and what will happen to the, say, this generator? Its price is reduced. Price of the demand will increase and price of the generation will reduce. Okay, and its price is increased. Generator number 2, its price is increased. The thing is that when there is congestion in the system, power is required to be taken from some costly generator. If there is no congestion, there is optimization, and what the optimization will do, it will take the power from some least cost generation. Maximum power it will take from some least cost generation. But in case of congestion, it has to. Now, there is a concept of market power. If a generator company knows that there is congestion in the system, it can increase its price, its bid up to any level, because the generation company can strategically know that the ISO has to purchase the power from me because there is congestion in the system. So that's why congestion is said to be one of the problems which is against the perfect computation. In order to have the perfect computation in the market environment, there should be no congestion. Congestion is required to be managed. Okay, and this is the problem of ISO, and this is the problem of researchers. So researchers can suggest different methods. Now, if the demand is flexible, case 4, this is the case 4. Case 4 is that demand at bus 3 is flexible, variable, and it gives bid. B3 is equal to 33 P3. This bid says that my maximum billing price is $33 per mega. I can add the maximum pay 33. Okay. Then what will after the in case there is congestion in the system, so the demand at bus number 3, the price is fixed at 33. It comes after optimization. After the solution of the optimization problem, what happens that this line is congested. It is having some mu value which is existing. Mu value of other lines is 0. And these are the price which the generator number 1 will get. P1 will have to generate 15 megawatt. This is the schedule. P2 has to obtain 10 megawatt. Okay, this is the price. So this is the case 4. So with these case 4 cases, what I want to explain that number 1, if the demand is flexible, then it can control the market price. Right. Number 2, it is also helpful in congestion management. Right. If anybody is having some query, then I will go to this. Then how to solve the problem with the Matpower. It's very easy to use the Matpower actually. Matpower is having many capabilities. Okay. Matpower is developed by Dr. Ray Zimmerman, which has who have done very nice work. It is very good for the researchers. Otherwise, we have to solve big problems, and a lot of time has been consumed. And sometimes we are not even able to code our problem properly in the MATLAB. Right. So this Matpower is becoming our task very easy. Task easy that it is solving the power flow and optimal power flow problem. It has developed a package of M files for solving power flow and optimal power flow problems. Basically, it is a tool for researchers and educators, but the utilities can also use this. It's a very nice tool which can be easily used in MATLAB. Nowadays, some open source Octave can also be used, which is open source for running the MATLAB. So for running the Matpower. So researchers can understand its codes and modify according to their problem needs. All the M files are available to the researchers. You can modify these according to your needs, but it's not very easy to modify them. So this is the home page from where the Matpower can be downloaded. So power flow and OPF, optimization power flow, can be solved by just writing run PF. Run PF is a M file which is used for power flow, and run OPF is for optimal power flow. Okay. You can go through this site and download Matpower, and then that folder, Matpower folder, can be placed in your current directory, and then open that folder so that it comes in the MATLAB path, and write this run PF and run OPF. It's very simple. All these are the, if you see this directory, these are the files which Dr. Zimmerman has developed. This is the whole, all the case files are also included, IEEE files, etc. It's not actually easy to modify it. but however it's very useful. Say run OPF in single quotes. I write the case 9. There is case 9. I think this is the it gives the results in a very formatted way. I have also made this problem in the MATLAB, and this is the case file which I have developed for solving the particular case which we are discussing. So this is my case developed by me, case 3 underscore getra. In order to solve this case, what I have to do, because this is DC OPF, run DC OPF, and case 3 getra, the case which I have developed, and it is giving me the results. And when I was doing my PhD, what I have done, actually, it was not easy to understand all these files. So I have developed my own tool for making changes in, say, objective function, for making changes in the constraints. Okay. I also given a name KDS power in that tool. So these are the files which can be made available in Matpower. I think you already know about Matpower. If someone from you know the Matpower, please raise a hand. Already you know the Matpower. It's a very nice tool. Up to now, if you have some problem.
All the number of buses, say if I want to do a 9 bus, some 5 bus, is that tool useful for all the number of buses?
Yes, it is. Some case files are already available. Say 9 bus, 30 bus, 14 bus, 118 bus. Number of case files are available. But if you have some special, means single line diagram according to your need, then you have to say case 3 which I am explaining here, that was not available. So what I have done, I have made some changes in the case file, and then I can run it. So generally we have to use 2 or 3 tools for solving our problem. Generally, because sometimes we become very sure that I am on the right path, but if we go for another tool, it says that there is something wrong which happens. So I have to verify my result, and this is one of the criteria. The reviewers are also saying you have to compare your results with the existing literature. So that's why 2-3 tools are required, but 2 tools are, I think 2 tools are sufficient. So now the last part of this my presentation is AMPL modeling language. It's also a very good tool. MATLAB is general purpose tool. Matpower is used for OPF and power flow, and AMPL is used for optimization. It is basically beneficial for the optimization, right? It is not beneficial for matrices. No, it's not beneficial for matrices, for the, say, finding out the inverse and other matrix manipulation. No, AMPL is not useful. AMPL is useful for the optimization, solution of the optimization problems. And we have to learn some special means terminology, some special symbols, and to code our problem in the AMPL. So in AMPL, you can visit the site www.ampl.com, and the student version is available. You can download the AMPL. Then some model files are also available there. You can first run those model. In AMPL, we need a model file and a data file and one output file. Okay, so one model file is required. These are sequence of steps which we have to follow for defining the model file. Number one is defining the model file, which is having the extension .m, then specify the data. Then solver is used to solve the model using solver. So specifying the model file and data file, these are two important steps. Model file requires 5 things in AMPL. Number one, it requires set. Set, you already know what is set. For example, in power system, bus is a set. Okay? Set means something which is having group, which is having number of similar members. So set is required. Then parameters are required. So in electrical engineering, we have RLC as the parameters: resistance, inductance, and capacitance. So parameters are required. Then again, decision variables are required, and objective function which is required to be minimized or maximized is required. Then constraints are. So 5 things are required in AMPL. If these 5 things are under our control, we can very easily solve the problem. So for this mathematical model, I've considered a model of the economic dispatch problem. In this model, what I am having is a cost function. This PGI is so this is PD actually. PGI is equal to PD, not PG. And there is lower bound and upper bound on the power generations for all the buses, all the generators, varies from 1 to up to NG. NG stands for number of generators. Okay. This is the MATLAB file which I'm giving here. Okay. To solve this problem, after optimization, I'm getting this result, and this is the model file of AMPL. With AMPL model and with the MATLAB model, I'm getting the same results. So set gen is a set because gen has, there are I think 5 members. There are 6 members in the gen. So gen is used as a set. Then param means parameter actually. I have to specify parameters. Here in this problem, I am having parameters as cost coefficients. So A, B, C as a cost coefficients. Then minimum and maximum values of the power available from the different generators is the parameter. And then the power load. Here I'm solving simple economic dispatch problem. I also taken P load as a parameter. And this is a variable only. The one variable P, which is means having a member as the generators. So specifying the variable as in the form of set. So P, J in gen. It should be greater than equal to P minimum and less than equal to P maximum. Very simply. The advantage of AMPL is that we can specify the different things as we are writing on the paper. Just write the model on the paper and you can easily code it in the AMPL. Okay. There is no need to represent in the form of matrices, but it is specifically for the optimization only. So this is the specification of the cost. What I write in the paper, minimize cost. So here I write minimize cost. So sigma AI PI square plus BI PI plus CI. Sum J and gen AJ star pj square plus bj pj plus cj. And then I get the constraint subject to this. So simply I write the constraint, subject to power balance. Sum of the pj is equal to p load. Right. So once some researcher understand the coding, it becomes very interesting to code any problem into the AMPL. Very easy also, but sometimes it becomes very difficult. So this is the specification of the data. Data can be specified as, first of all, we have to specify all the sets. Generator is a set, we specify the set, then we have to specify the parameters. Right? So all the parameters A, B, C, P min and P max are specified. The first column represents the generator number. And then simply write the solve. And whatever you want to display, it is written as display P and cost. And it will then again give me all these results. I verified that the results which are obtained from AMPL are same as from MATLAB. So I think I have explained the three things here. So these are certain concluding remarks for this presentation. OPF and CM are the essential functions of the ISO of electricity markets. So in this talk, OPF and CM problem formulation have been discussed. The use of computational tools becomes very necessary to carry out scheduling and congestion management in electricity markets. So in this talk, we have used three tools: MATLAB, Matpower, and AMPL for the OPF and CM. So I have very shortly explained all these things, but actually these are not the complete things which I have given to you. So just I have given you that there is one way ahead. You can actually search that way. If you go for that, you will find very many new things there. Thank you. If you have some queries, please.